Hello and welcome everyone to the York Observatory's weekly Teletube broadcast, the online and astronomy astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. We broadcast every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle at York Observatory and Facebook at Alan I. Carswell Ops. I am Maheen, and I'll be one of your hosts this evening along with Dr. Hyde, Matt, Laur, and Tina. Tonight, we have a talk on detecting signs of life on a distant planet from a special guest speaker, Dr. Sarah Rugheimer, whom we will introduce later. Welcome again, everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week. Tonight, right after sunset, we have Venus visible near the western horizon, which looks like a very bright star in the night sky. And on the lower right of Venus, we have Mars, which will be visible only until 9:50 p.m., and so it might be a little hard to catch. Arcturus, the red giant branch star, is also visible, and Antares, the brightest object in the constellation of Scorpius, is a good catch for tonight as well. The Moon is currently in a waning gibbous phase with an illumination of 81.09%. Just a heads up that the annual Southern Delta Aquarids meteor shower will peak before dawn tomorrow, that is Thursday, July 29th. They seem to originate near the bright star Delta Aquarius in the constellation of Aquarius. I must also mention the Jupiter's opposition to the Sun on the night of August 19th to 20th, which will be a great event. So stay tuned for updates on some great live observing with our 1 meter telescope. Also, sorry for the fact that we don't have live viewing tonight because of the bad weather. However, do join us next Wednesday to enjoy some live viewing as well. Now, without any further delay, I will hand it over to Dr. Hyde to introduce our guest speaker for tonight.
Hello, thank you very much, Maheen. It's a great to know what's up tonight, even though the clouds might be blocking our view just a little bit. Now, it is my very great pleasure to introduce Dr. Sarah Rugheimer. She is an astrophysicist at Oxford now, but she will actually be joining the astronomy faculty at York next summer. So, as a way to sort of whet our appetites, if you will, we're actually going to get a remote talk from her for this show. So it's very lucky because she works on how to detect life on an exoplanet, looking at atmospheric biosignatures and all kinds of other great stuff that you're going to hear about in her talk shortly. So I'll try not to spoil too much about it. Her research interests include modeling the atmosphere of climate of extrasolar planets with a particular focus on atmospheric biosignatures. So, very fun stuff. If you want to research her a little bit more, you can actually find her 5-minute TED Talk, which is online, as well as all kinds of other great outreach that she's done. She has a new astrobiology course available for the public on Amazon Audible Originals, which I have not realized you could put courses up there, but she has done it. So if you want to check that out, make sure to head on over. And I'll just go ahead and say, take it away, Dr. Rugheimer. Now we're going to go over to her talk here shortly. And this is a live pre-recorded talk due to, of course, the large time difference that we right now have with Oxford. So let's go ahead and pull that on through.
Hi, my name is Sarah Rugheimer, and I'm a researcher at University of Oxford, but I'm actually joining York U faculty next year. So I'm excited to be here for the Wednesday's Teletube from York University's observatory. I am going to give this talk asynchronously from you as I'm in the UK. So it's after midnight when you usually have your live sessions. But I hope that you enjoy the talk. And if you have any questions, please reach out. So I'm just going to share my slides now. So the talk that I want to give today is detecting signs on a distant planet. This is my research. I'm really interested in this question of, are we alone in the universe? And so there's been this search for extraterrestrial intelligence called SETI, and it's searched for 60 years or so, and it's really just, we haven't seen that hello Earthlings call yet. We've really just been met with silence. And so my question is, are there aliens out there? And when I think of aliens, I'm not really thinking about these guys. I'm thinking more about microbes, just single-celled organisms. Could we detect those on another planet? And indeed, if an astronomer were looking, an alien astronomer were looking at Earth, they would see this blue dot. And so this was the first selfie taken by Voyager about 6 billion kilometers from Earth. It turned back and took this picture. And aliens would be able to see signs of microbial life, especially in our atmosphere. And so the light that they would see would be broken up into a spectrum, and each of the elements has a unique fingerprint. And this is basically how we can detect these molecules in the atmospheres of other planets, by looking for these unique fingerprints of molecules. So if we were to look at Earth's spectrum, this pale blue dot, we would see signs of oxygen, ozone, methane, carbon dioxide, water, and even signs of vegetation. And so these are the sorts of things that we want to do when we look at other planets. And we've actually found some really interesting systems. So you might have heard of the TRAPPIST-1 system. That's a system with 7 planets. They're all similar in size to Earth, and 3 of them are in the habitable zone. What's incredible to think about this system is, because the star is much smaller and cooler, the planets are closer in. And so if you were standing on the surface of one of those 3 habitable planets and you looked in your night sky, the other 2 planets that are habitable would be the size of our moon in your night sky. So maybe you could even see continents and oceans standing on one of those planets. But we do have these challenges to overcome before we make this detection. So I think of exoplanets in general as having 2 main challenges. We have a technological hurdle to overcome, and then we have a second one, which is the interpretation of what we're finding. And so often when I talk about finding alien microbes and other forms of life, I think most people, envision, and even I do, this planet with all sorts of complex life and vegetation, sort of like out of Avatar, and what theorists like myself claim we're going to find is a nice spectra with easy to define features, clear signs of life. And the reality is, it's going to be hard. It's not going to be so easy. We're going to find a pale blue pixel. There's going to be a lot of error on each of the measurements, and there could be multiple models that fit what we detect. So that's going to make it difficult. And the technological hurdle is a bit like trying to find a firefly in front of a spotlight. But imagine that spotlight is where you guys are in North America, and we're observing, say, from Europe. And that's the feat that we're trying to overcome, being able to tease out that size. And in fact, it's even 100 times more difficult than that. So this is why there's this technological hurdle. But what's amazing is that we're actually starting to overcome that hurdle. And the first telescope that will be able to detect atmospheric molecules in other planets orbiting other stars is the James Webb Space Telescope. And this is launching later this year. And then there's these large ground-based telescopes like the ELTs, they're called extremely large telescopes, and they will also be able to make some of these measurements. When I think about these 2 sorts of missions, the ground-based ones and the space-based ones, there's really trade-offs between which is best for looking at exoplanet atmospheres. In space, you have a lower resolution, but you're able to get the abundance of the molecule. So how much is there? And that's really helpful when we want to try to contextualize what we're seeing and interpret what we find. Now, from the ground, we can't do that. We can't get the abundance so easily, but we can see presence of molecules, and even more minor molecules, even isotopes, which I'll talk a little bit about towards the end of the presentation. So there's advantages that we can detect more finer molecules that don't have as high of abundance in an atmosphere with this high resolution spectroscopy technique from the ground, but in space we're able to get the amount of the molecule. just want to briefly take, kind of a look back at time just in our own technological improvements through the ages. So this was the image we had of Pluto in 1930. And that basically looks like what exoplanets look like to us. And then with the Hubble Space Telescope, this was the image we had in 1994. And then after some updates to the Hubble, we had this better image of Pluto in 2003. And this is a bit of an unfair leap because now I'm talking about a flyby mission, but with New Horizons, we could actually see snow-capped mountains on the surface of Pluto. And similarly with Jupiter's Juno mission, we've been able to see much more complexity in Jupiter's atmosphere and learned more about the atmospheric dynamics that are happening in gas giant planets in our own solar system. So as we are able to overcome some of these technological challenges, we can see more physics and try to put that into our models and understand exoplanets even more. There's basically two ways to search for life. We can look for life as we know it. So that's things that are the main biosignature molecules that are on Earth: oxygen, ozone, methane. There's a few other ones, some sulfur compounds and methyl chloride, nitrous oxide. And then there's molecules that might be a different type of life. This is life as we don't know it. And so one is certainly easier to do than the other because we might be able to recognize it, but we want to try to be open to the possibility of what we might find. So this goes back into this interpretation hurdle. And what I want to point out is that it's really difficult to not fool ourselves into what we're seeing. And so Richard Feynman has this quote, which is, "Science is a way of trying not to fool yourself. The first principle is that you must not fool yourself, and you are the easiest person to fool." So I think this is important when we think about really any finding in science, is that we have to try to overcome our confirmation bias, trying to see what we want to see. And that's why these discoveries, as they're announced, more teams will try to verify them. And this is how we're able to confirm new discoveries. So going back to where the difficulties lie, though, the image is going to be difficult to interpret. It'll be this pale blue pixel, and this is an actual image of an exoplanet, and you can see it kind of resembles that image of Pluto that I showed you earlier. There really is only one type of detection of life that would be unambiguous, and that would be this SETI "Hello Earthling" signal. That's life. Everything else is going to be harder. We're going to have to try to tease out signs of geology and physics and chemistry from biology. And so that's this interpretation hurdle, and that's really where my research focuses. So the technological hurdle is just, can we detect these molecules? And then the second one is, what do they mean? So I want to start by showing that Earth has been many planets. We tend to think of it more or less as it is now, but Earth has changed over its 4.5 billion year history. It has been a hellish Hadean lava sort of world, an Archean world with tidal pools and hotspot volcanism. It's gone globally glaciated several times. Then you had the Triassic period and other eras where you had even large insects like dragonflies that are 1 meter in wingspan. And so Earth itself has had massive changes and can represent to us many types of planets. And to think about this, we could think about the history of life on our planet and break it down into 1 hour. So at 0 minutes into the hour, you have the formation of Earth. And then the origin of life is about 9 minutes into the hour. So Earth had to cool first in liquid water. We don't exactly know when life first started on Earth because a lot of the rocks have been destroyed from plate tectonics. They're just brought back into the mantle of Earth and we're not able to access them. But we do think that the origin happened very early because we have signs of life dating back at least 3.5 billion years, if not 3.8, and there's even a claim at 4.1 billion years ago, signs of life. So that's 14 minutes into the hour. Oxygenic photosynthesis, that took a bit longer. And that was the rise of oxygen before the rise of oxygen. And that was about 25 minutes into the hour, at least by 2.7 billion years ago. We have clear signs of oxygenic photosynthesis. But then life remained single cellular for most of the time. And so until just a billion years ago, it was basically single-celled microbes living in microbial mats, and there wasn't really complex life. That's 47 minutes into this hour. We didn't have signs of land plants, and that was only a half a billion years ago, or 53 minutes into the hour. And then anatomically modern humans, that's humans that you would recognize, brothers and sisters, they're around 300,000 to 250,000 years ago, or the last second on this clock. So my research is, how can we detect biosignatures around other stars and at different geological times? Because the Earth itself has changed. We know planets are going to look very different from Earth as well, and we want to try to tease out what these features are. And so if we think about all stars within our stellar neighborhood, within 33 light years, most of them are M dwarfs. So this is a schematic of that. So the G-type stars are stars like our sun. Those are the yellow dots. There's about 20 of them in our 300 closest neighbors. But the M stars, that's 75% of stars. And those are those red dots on this schematic. They by far make up most of what is nearby and in our universe. And so we want to know, are those planets habitable? Are the planets orbiting these stars habitable? And Kepler found, unfortunately, Kepler passed away a few years ago, but before Kepler did, the Space Telescope found that 1 in 4 M dwarfs have a habitable planet. And that's really exciting, because that means there's so many places for us to look for signs of life on exoplanets. But M stars have some difficulties. And then one of the main difficulties is they have really strong flares, and the planets are close in, so it could strip away the atmosphere or even sterilize the planet from all life. And how this would work, also is they can make gases that we associate with life, but it wouldn't actually be coming from life. So one example is this. So say you have an early M dwarf and it's very active, and say you have a planet orbiting that M dwarf. The high energy extreme UV light would break water in the atmosphere into hydrogen and oxygen. Hydrogen is light, so it escapes the atmosphere, and you're left behind with an oxygen-rich atmosphere. And the planet has also lost its water and is dry. And depending on how much oxygen reacts with the surface, you could see some oxygen, maybe thinking it's life. And so this is why there's no single gas that's enough, because of these false positives of oxygen that we're learning more and more about. So when we think about stars, because the different star types will matter, you have your hotter stars and you have your cooler stars. And in general, the hotter stars have more UV, and UV will destroy some gases like methane, for example, making it harder to see around those planets. But then UV also produces other biosignatures like ozone from oxygen. And ozone is a lot easier to see and is a proxy for oxygen. So we want to go after that gas as a detection. And on Earth, those two gases together, oxygen or ozone in combination with methane, make a very strong biosignature. And this is because, like I said, you could get oxygen or ozone alone if you break apart water or CO2 with extremely high energy UV light. And you can get methane without biology from volcanoes. And so either of these two gases alone are not good biosignatures. But biology produces large quantities of both of these gases on our planet. And so if biology were to turn off tomorrow, though, these gases would react very quickly, and they would no longer be in our atmosphere at such high quantities. And so this is why it's this combination of those two gases that make it a strong biosignature. And indeed, it's been pointed out for many decades that it is this combination of oxygen and methane on Earth that is the strongest biosignature feature to an alien astronomer that we're, say, taking a picture of our planet and trying to tease out what's happening in our atmosphere. All right, so going back to these ways of finding alien life, we want to think about alternative ways to find life as we don't know it, that second way. And one of the best ways I think we can do this is by first going in our solar system and looking. On an exoplanet, it's really going to be hard to distinguish even life as we know it from a distance, from light years away. And so in our own solar system, we can look in places with vastly different biochemistries, such as on Venus or on Titan. Or we can look for life maybe with sort of similar conditions with water and chemical rock interactions on Europa and Mars. And these would be great places. All of these are great places to see and test these ideas. And you've probably heard about Venus in the news. There's back and forth debate over whether there is even this gas that could be life. Is that gas even there? It might not be. It might be a misdetection. If it is phosphine, could there be life surviving in that inhospitable environment? The temperatures are so hot. And also on Venus, there was just a paper came out last week that showed that the water activity in Venus's atmosphere is so low. And what water activity means is one thing it matters is how much complex chemistry can happen in that water activity. And it's just very low. It's way lower than anything that we think that could survive or could even have complex chemistry. So these are the sorts of questions, though, that we want to pursue, because if chemistry is happening in a very different way, we might be able to explore it on these environments that we could actually send probes to and actually look at these, in situ measurements with future missions. So the other way to think about life as we don't know it is we can think about any type of molecule that life could produce. And there's a lot of them. So there are 16,367 molecules that could be produced by life and could exist in an atmosphere. The problem is we don't have the spectra for most of these molecules. We only have spectra of even poor quality for 0.04% of the 16,000 or so molecules that could indicate life. And so even if they were there, we couldn't see them. And so that's a problem. So we need to better fund these laboratory and theoretical measurements of how to find life and find these sorts of molecules, and even and molecules that don't indicate life. And I like this quote from a colleague of mine and friend, Clara Sousa Silva. She says that light from an atmosphere can tell us so much. What we're seeing, could indicate oceans or life, but without knowing what each meaningful molecule looks like, that life is indecipherable. And so this is an example. That plot down below, you have the blue lines and you have the red lines. So the red lines are our old knowledge of ammonia, and the blue lines are updated calculations with more lines. And so you can see how we had some of the lines we already knew, but there were many more transitions and fingerprints of that molecule that we didn't know. And ammonia is a very well-studied molecule. So, and this really helps us with our observations. So there is this methane dwarf example that I want to show you, where we had observed this spectra, and when we tried to fit it with our experimental measurements for methane, this was the fit that we got. And this was using 350,000 known spectral lines for methane, which seems like a lot. But then when they put in the billions of lines that were calculated from exomol, theoretical quantum chemistry calculation, then we could fit the spectra. So getting higher quality measurements of just these molecules is a really important step in us being able to distinguish a gas on another planet, because we just otherwise don't know what we're missing with those lines. So your observations are only as good as your models, and your models are only as good as your line lists is kind of the main message here. So in astronomy, we have multiple things that we can do, and we want to make these observations, but there's still a lot of theoretical work that needs to be done so that we can interpret these observations. And also why this is important, when we go from, say, 350,000 lines to 10 billion lines, we can detect these more minor molecules using a technique called high resolution spectroscopy. And so this is where we see the Doppler shift of a planet going around this star, and then the lines actually are moving from the atmosphere. And what this does is, if you look on this gray panel here, the spectral lines of carbon monoxide in this case are going in a sinusoidal way across the spectrograph. And how we're able to see that is actually the planet moving. So we're able to see that shift in the lines just from its velocity. And this is really helpful because what that shift allows us to do is see through our own atmosphere. So the lines, say, of carbon monoxide in our own atmosphere would not be moving. And then the planet lines are moving because of that velocity. So this is basically how this works. When you have these shifted lines, as the planet's moving towards us and away from us, you'll have red shifted and blue shifted lines on your spectra. And this is what we're seeing. You can actually track that motion on the spectrograph and see the fingerprint of the line. And what's amazing is that with this technique, we could not even detect the presence of molecules, which I think is incredible in and of itself. But we can also detect just the difference of one neutron. So this is, say, hydrogen is just a proton and electron, and deuterium is a proton plus a neutron and electron. And those just the hydrogen versus deuterium lines are different enough at high resolution for us to be able to detect them. So this is really exciting. So you can see here the blue lines are carbon monoxide with C12. So that's carbon with 6 neutrons. And the C13 has an extra neutron, and that is in the orange lines. And at high resolution, the spectra is different enough such that we could actually distinguish those molecules on an exoplanet atmosphere. And what's really cool about this science is we could do this now for hot Jupiters on VLT with CRIROS Plus, and we might be able to do it in the future for our nearest known exoplanet that is small on Proxima Centauri b. We could maybe detect heavy water or HDO instead of H2O. And that would be detectable with the extremely large telescope in just one night of observations. And how we do this is we need to know the high resolution, but we can march our observed high resolution spectra against a template of that molecule. And when they overlap completely, you get a nice detection of that molecule. So that is kind of the summary of what I wanted to talk about today, to basically just say that we're actually really getting close to overcoming these technological hurdles. We're going to have our first chance in the next few years with James Webb launching hopefully this year, and Ariel launching later in the decade, as well as these large ELT missions. And the biggest one, ELT, is 39 meters, and it's going to have a high resolution spectrograph called METIS, and it's coming online in 2025. And these two together will be that first step that we can make. And then on the 25-year horizon, there's some really exciting telescopes that are going to be going. So this is the telescopes after James Webb, and these are things like LABORAT or LIFE. These are really large telescopes that would be in space that could do this for many more planets. So I would say in the next decade, we're going to have the chance to characterize maybe a handful of habitable exoplanets. But over 25 years, then we're going to be able to start getting more statistical, higher numbers of planets and try to tease out some patterns maybe of what we're seeing. And that'll certainly help with these interpretation hurdles. Here's the spectra for Earth, Venus, and Mars. Those spectra you can see are very different for our 3 terrestrial planets in our solar system. And so we expect the planets around other stars to also be different and to be a whole variety that we can't even anticipate yet. And so we want to be able to distinguish those as well. And ultimately, in doing so, we want to find these molecular fingerprints of life. I want to leave you with a question, though. So even if we're not alone, even if we find life, microbial life, on another planet, will we be satisfied? Because everything I've talked about today is really for microbial life. And so would that be satisfying to us to find microbial life on an exoplanet? Even complex life, like a ladybug, that's a very complex life forms taken billions of years. And that's not something that we can communicate with. We can't have a conversation about philosophy or exchange technology with a ladybug. Would that be enough? Do we really want that intelligent signal So my question to you is, will we still be lonely, even if we find signs of life on another planet? I hope not. I hope that we'll be really excited about this discovery, because I think it's one of the most exciting moments in human history. And for that journey, I'm really looking forward to the next decade to see what the sorts of observations come in, and even in the future decades to see even more telescopes that will be able to do this for more planets. Thank you so much for having me here today. I really hope you are all doing well, and please send along any questions. I can try to answer them in a Word document or something. All right, bye.
Thank you so much to Dr. Sarah for giving us such an amazing talk. We will now move on to her answering some questions sent in by the hosts this evening.
Thank you so much for submitting questions to my lecture for this public lecture at York. I am going to answer them remotely. Sorry, because of the time change, I can't answer them live. So from Maheen, sorry if I apologize if I pronounce anyone's name wrong. There's two questions. What doors does the discovery of microbial life on another planet open up for the scientific world? This is a great question, because I think really, if we discover life on another planet, it really opens up the phase space where we think that life could evolve and live. So where and what are the conditions that life can originate? Where can it live? Did it happen once or many times? The origin of life, is it rare or common? These are all sorts of questions that we can start to probe if we find the evidence of microbial life on other worlds in the solar system or on other exoplanets. The second question was, since the fingerprints of elements help in the identification of molecules in different atmospheres, could this play a role in the discovery of new unknown elements? So we can't actually discover a molecule that we don't have the spectra for. So in this sense, no, we're kind of necessarily hamstrung to only look for things that we can identify. And even the molecules, something like methane, took a long time to figure out all of those high resolution spectral lines. This is work done by, for example, the ExoMol team here in London, or other people around the world doing laboratory experiments. My friend, Dr. Clara Sousa Silva, she works on this as well, and she's given many public talks as well. And this is a really needed area of science, because we won't be able to identify something unless we have the spectra for that molecule, and we don't have the spectra for most molecules. So yeah, so we need to do that work to get the spectra, but we would not be able to identify things that we don't have a template for our models. However, I would say we can predict the types of molecules that would form in different planetary systems from, under different pressures and temperatures, from chemistry and geology and things that we know in doing laboratory experiments on Earth. From Christina, do we expect to find different DNA units in these extraterrestrial microbes? Yes, absolutely. I doubt life anywhere maybe uses DNA, except for Earth life. It would be odd to me to assume that DNA is the only or most common form of information molecule, because there's many other types of molecules that can form information. There's a great book, which I'll recommend later, which goes through a bunch of different types of information carrying molecules. There's also things like PNA or TNA, RNA, all of these sorts of molecules, PAWS, these can all create and carry information. So I doubt DNA in its exact form exists on other planets, but life uses some form of coding, because that's how life is able to adapt to new environments and carry on and pass on that heritable information to the next generation, so that they can also compete for nutrients, resources, and energy, which is what life does. How can we learn more about the intersection between biology and physics in the search for extraterrestrial life? Great question. So I have a bunch of books that I'm going to recommend here. My favorite book that got me into this field is called Genesis: The Scientific Quest for Life's Origin, and it's by Robert Hazen. I'd really recommend it. Also, The Origin of Life by Adam Rutherford, Nick Lane, The Vital Question. There's a new one out called The Zoologist's Guide to the Galaxy, What Animals on Earth Reveal About Aliens and Ourselves. Dave Deemer has two books that I really like, First Life, as well as Assembling Life. And so he does a lot of prebiotic chemistry, whiting, drying cycle, clay reactions. Just an overall great book on habitable planets and also chemistry and biology is How to Build a Habitable Planet, the story of Earth from Big Bang to Humankind. Recommend. It's like meaty, but well written and easy to understand. And just like in general, as a science book, I really love Carl Sagan's The Demon Haunted World, just about the scientific process. It's probably my overall favorite book on the scientific method. And then also I have a course. It's on Amazon Audible Originals. It's called Searching for Extraterrestrial Life. It's an audio course. It's 5.5 hours, so you can also check that out. And that's just more details on it. Really, that course specifically goes more into prebiotic chemistry, biology, evolution, as well as astronomy and how those all link together. From Matt, if the presence of phosphine in Venus is not a misdetection, wouldn't this example of life in such a hostile environment give us a broader perspective of where to find life? Absolutely, of course. Yeah, I mean, this is one of the things that what makes Venus so exciting. If there's life there, it completely changes our understanding of where life could live, because just doing chemistry in that environment is hard. It's not just like biology. It's not like we haven't thought of where biology could live. It's like, can chemical bonds move in a solvent? In those clouds and in those highly acidic and hot temperatures and pressures and environments, or in the upper atmosphere in a diffuse environment. This is a real problem just for chemistry, let alone biology. So I would say, yeah, it absolutely would change how we think, where we would see and look for life. So I think it's vital that we go back to Venus and look for it. It's looking more and more likely that perhaps the phosphine isn't phosphine, or it's from a different level in the atmosphere if it is. So I'm not really hopeful that this is going to turn out to be life. However, if it does, amazing. And even if it just turns out to be phosphine and it's from a geological process we don't understand, or a photochemical process we don't understand, that's also really important for us to better understand what types of environments can form under very different planetary conditions. And then Matt also asks, according to you, what would it mean for humanity to find life on another planet? Even if it's just microbial life, do you think it would impact how we see the universe? Yes, I do. This is one of the reasons why I'm in the field. I think it would prove, for one, if we find life on other planets, even just one other planet, it would prove that life is really everywhere. You know, right now, we just don't know. We think life is everywhere by virtue of this, the mediocrity principle. We're nothing special. We're on a normal star, in a normal galaxy. It's been around kind of a normal length of time. So we want to know if life is something that has only happened once in the universe or many times. I think most scientists like myself assume that it's happened many, many, many times. However, we just don't have data one way or another on that question. So that's one thing, is actually proving that. And then, of course, detecting complex or intelligent life would be a further step in understanding our place in the universe. It's sort of like before 1992 and 1995, when we found the first exoplanets, we thought there were probably planets around other stars. I mean, this was thought to be true, but we didn't have evidence of it. We just had the solar system. So it is important to do that detective work and actually find the evidence of exoplanets around other stars, or in this case, of life around other stars. And then from Laur, does Venus have a magnetosphere? If so, is there a reason? So Venus doesn't have an internally generated magnetosphere, and this is in part because it has a slow rotation. It rotates only once every 243 days. And so because of that, it doesn't have internal thermal convection. And so it doesn't have like a liquid metallic part of the core that's moving fast enough to generate a global magnetic field. There is a weak magnetic field on Venus that comes from the interaction of the solar wind with the upper atmosphere, and it induces some current and magnetic field from that. However, that's not really kind of the magnetic field you're thinking of. And it's not like Earth. And then the second question from Laur is, what precise chemical composition is to be found in the atmosphere? How did Venus's runaway greenhouse occur? We don't know. So, I mean, there's of course theories on how this happened, but there's a lot we don't know about Venus and Venus's history, which is why we need to go back and explore more. So NASA selected 2 missions recently, Da Vinci, which will measure the composition of Venus's atmosphere and understand how it formed and evolved, as well as determine if Venus ever had an ocean. And then Veritas will map Venus's surface to better understand the planet's geological history and understand why it developed so differently from Earth. So these are missions that are hopefully going to answer that question for you. Thank you so much for these questions, and I look forward to meeting you guys in person next year. All right, bye.
Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly Teletube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening were Dr. Hyde, Maheen, Tina, Laur, and myself, Matt. Special thanks to our guest speaker tonight, Dr. Sarah Rugheimer, for giving us such an amazing talk and answering all of our questions. And make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. All of our programs are free, but if you would like to make a donation or buy one of our observatory calendars, which by the way, they are now at 50% off, so don't miss that. You can see our website at observatory.info.yorku.ca. And you can always connect with us with on Twitter with the handle @York Observatory, and check out our website for show notes, content updates, and contact info, as I mentioned before, at observatory.info.yorku.ca. Thanks for tuning in. Clear skies and have a great night.